Imagine you're training a convolutional neural network, a type of network that is heavily reliant on the training data to avoid overfitting and poor model performance. Or imagine you're performing image recognition using deep learning. How do you find sufficient images for training? How do you collect enough data? The accuracy of your model is directly dependent on the quality of your training data, but unfortunately, in many cases, only limited data is available. Gathering data is often very challenging and expensive. Well, a solution for your problem is data augmentation, a data space solution to the problem of limited data in computer vision, which can improve the performance of AI models and expand limited small datasets. In the following minutes, we will dive into this. What is data augmentation? We will start with a small introduction and afterwards we dive deeper into common data augmentation techniques for images.
What is data augmentation? Data augmentation is a technique of increasing the size of data used for training a model. It's the creation of fake data to avoid the model overfitting to variability in the data that's not relevant. For reliable predictions, the deep learning models often require a lot of training data, which is not always available. Therefore, the existing data is augmented in order to make a better generalized model. The original data can be reused multiple times, each time with a small transformation. Both offline and online augmentations exist. The transformations should relate to the variability in the real world, and the transformed data must still be realistic and correspond to the original label. Offline augmentation creates augmented samples for each original sample and stores them on the disk. It saves computing time during the training process when training multiple models or when using iterative learning approaches. The storage limitations restrict the number of augmentations. It's typically used for smaller datasets or when there is no support by any tools. Online augmentation creates augmented samples during the training. Each sample is augmented on the fly before using it in learning. This asks additional computing time, but each augmented sample is different. It's typically used for difficult tasks with lots of variability, where even a lot of data is not quite enough. It's part of the standard tool flow in deep learning frameworks. Data augmentation creates more data and makes the model more robust to variability. However, it makes the problem more difficult and probably needs a more complex model because of this. New data still needs to be similar to the old data, and the augmentations are only applied on the training set, never on the testing set.
There are several techniques of data augmentation that can be used to create new training examples. The most commonly used techniques include flipping horizontally or vertically, rotate, zoom in or out, crop, change color or sharpness, or delete a part of the image. This helps the model to recognize objects in different sizes, angles, context, and lighting conditions. For the same purpose as data augmentation, synthetic data can also be used. This refers to artificially generated data that simulates the characteristics and statistical properties of real-world data using algorithms or mathematical models. This is mostly used when real-world data is scarce or expensive.
Let us now discuss some more advanced data augmentation techniques for images. First of all, you have adversarial training. This is a technique that starts from the current state of the model and then it takes an input image that is already correctly classified and adds strategic noise to it up until a point that it is still the same image for us humans, but is differently classified by the model. This augmented image is then added to the training set to make the model robust to these kind of attacks and faults. A second, more advanced technique is using GANs to make new images. GANs or generative adversarial networks are a machine learning technique that, given a set of input images, can create images that are very similar to this one, and this can be used to extend a given data set.
Neural style transfer is used to combine the content of one image with the style of another. It's somewhat similar to a color transformation, but it separates itself with the ability to transfer textures and other miscellaneous distortions that are impossible with classic color filters or affine transformations. A series of convolutional layers in a convolutional neural network model can be deconstructed such that the content and style can be separated. That separation forms the Gram matrix, which can be used as a loss function for a generator network. To use this technique in data augmentation, a series of label-preserving transformations is applied to improve the quality of the dataset. Style transfer helps the network learn better features for transfer learning. It introduces more variations into the source domain by augmenting the data, enhancing the overall robustness of the model. It's used to generate new images with the same content but a different style.
Finally, we are going to discuss the limitations of data augmentation for images. As explained before, data augmentations can help with certain problems in the data, but there are also problems that cannot be fixed by data augmentation. An important one is bias. If there is bias in the original data, then this cannot be fixed by augmenting the data. When a model that predicts the age of a person is only trained on the images of adults, then augmenting the data will never magically make the model able to predict the age of children.
While data augmentation can be an effective technique for improving the performance of machine learning models, it is important to be aware of the potential problems and pitfalls that can arise from its use. Data augmentation is not a one-size-fits-all solution, but appropriate techniques for a particular application should be used to ensure that the augmented data covers a wide range of realistic scenarios the model might encounter in the real world. Otherwise, unintended bias could be introduced into the model. For example, in the case of dogs, flipping images horizontally may be a useful transformation, but flipping them vertically or upside down may not be. This may result in a dog's leg or tail appearing where its head should be, which could make it difficult for the model to recognize the dog correctly, and may produce bias or confusion in the model's predictions. Another example might be a dataset of digits. Rotating the number 9 by 180 degrees would result in a new image that looks like the number 6, but would still get the label 9. This can lead to problems in our machine learning model, especially because the number 6 and number 9 have different meanings. This type of problem becomes even more clear with an example that differentiates lemons from limes. Changing the color as a data augmentation technique is clearly not an appropriate tool for this application. To make this all a little more clear, we've included a small deep learning example where we will train the model to recognize different digits. We started by importing the needed libraries and used the MNIST dataset from Keras, which is a dataset of handwritten digits. To make the effect of the data augmentation more clear, we decided to make this training set a bit smaller. The deep learning model we used is a very basic image recognition model, and we included a visual to see how it works. The model works with different layers, where each layer will recognize different aspects of the images, like the edges or the color. After we constructed the model, we trained it with the original smaller dataset. These results show very clearly that the model suffers from overfitting. We get a very high training accuracy, but a low validation accuracy, because the model can only recognize the small set on which it has been trained. To fix these results, we decided to use Image Data Generator to do data augmentation on our training set. Because we are dealing with digits, there are a few transformations that we can't do, since these would result in bad data points, as we explained earlier. That's why we can only rotate over 15 degrees, and we don't allow horizontal or vertical flips. After doing the data augmentation, we trained the model again, and we used early stopping so that the training will stop once the validation loss is small enough. When we look at the results with data augmentation, we can clearly see that this model has been trained well, without overfitting. The validation accuracy is as high as the training accuracy. This means that the model is as good at recognizing training examples as it is at recognizing new examples.
In conclusion, data augmentation is a very powerful technique to improve dataset size and quality. There are many techniques, of which some are more advanced than others, but in the end, the person training the model should still have some thought on which data augmentation techniques are applied.